Now I will illustrate the method of solving another class of ODEs. This class of ODE, the equations are not linear, but we will reduce them into first order linear ODE, and then you already know the method of solving a first order linear ODE. This kind of equation is called Bernoulli equation. So the Bernoulli equation is of the following type. Consider dy by dx plus pxy is equal to qx y raised to n. This is a Bernoulli equation where px is a function of x and qx is a function of x. So this is not linear because y raised to n appears here, and when n is equal to 0 or 1, this gives us a linear equation. But if n is anything other than 0 and 1, then it is not linear. So we assume that n is not equal to 0 or 1. In that case, we can transform this given Bernoulli equation into a linear form by substituting v is equal to y raised to 1 minus n. So we replace the variable y here and introduce a new variable v is equal to y raised to 1 minus n. So if v is equal to y raised to 1 minus n, then dv by dx will be equal to, in bracket, 1 minus n and y raised to 1 minus n minus 1 dy by dx. So that minus 1 and minus 1 cancels, and we get dy by dx is equal to, that is the term here, is equal to this brought on the denominator. So 1 by 1 minus n and y raised to minus n brought here. So it will be y raised to n dv by dx. So dy by dx is equal to 1 by 1 minus n y raised to n dv by dx. So in this differential equation, we substitute dy by dx with this. So we get dy by dx got replaced by the term that we obtained here. So we got this, but the rest of the equation remains as it is. Px y is equal to qx y raised to n. Now you divide this equation by y raised to n. So what we get is 1 by 1 minus n dv by dx, because we are dividing by y raised to n. This y raised to n goes away from here. Then we have px, then we have y multiplied by y raised to minus n, that is same as v, and then we have is equal to qx, because y raised to n we have divided by y raised to n, so this term is cancelled. So the equation that is appearing here is a linear first order ODE. So when you are dividing, we assume that y is not equal to 0. So you bring this 1 minus n on the numerator by multiplying this by 1 minus n. So this is how it looks, and this is a linear ODE in the dependent variable v and independent variable x. So we can solve this linear ODE by method that is known to us. So this is how you can solve a Bernoulli equation. So we take an example of a Bernoulli equation. So the given Bernoulli equation here is dy by dx plus y is equal to x y cube. This is not linear because y cube appears here. Y is the dependent variable. For linear equations, you have the dependent variable and its derivatives appearing with maximum power 1, and they should not appear as a product. But here the power 3 appears for y, so this is not linear. This is in fact a Bernoulli equation. So in Bernoulli equation, y raised to n can appear, so that n is 3 here. So we know if the n is 3, then the change of variable that we make, that is we introduce v to be equal to y raised to 1 minus n. So n is 3 here. So 1 minus 3 is minus 2. So v is equal to y raised to minus 2 appears here. See here, it was y raised to 1 minus n. So it is y raised to minus 2 is v. So we differentiate this. We get dv by dx is equal to minus 2 times y raised to minus 3 times dy by dx. So we can rearrange the terms and we can substitute in this differential equation. So in place of dy by dx, we can write minus 1 by 2 y cube dv by dx. And then we can divide the entire differential equation by y cube. So this is what you will get. The y here multiplied by y raised to minus 3 will be y raised to minus 2, and that is v. So this is how the given equation will get transformed into. And on taking that minus 2 in the numerator, that is multiplying this equation by minus 2, what we get dv by dx is equal to minus 2v. dv by dx minus 2v is equal to minus 2x. This is a linear ordinary differential equation of first order in the variable dependent variable v and independent variable x. We know how to solve it. We have to first find out the integrating factor. The integrating factor is e raised to integral px dx. So here px is minus 2. So the integrating factor is e raised to minus 2x. The solution will be dependent variable v times integrating factor, that is v e raised to minus 2x is equal to integration of integrating factor times qx dx plus c. So it is minus integration of 2x e raised to minus 2x dx. The e raised to minus 2x is the integrating factor which is appearing here as well as here. Now this can be solved by integration by parts. So we keep x as it is and integrate e raised to minus 2x. So we get 2x e raised to minus 2x divided by minus 2 and then a minus sign, and then here we differentiate x, we get 1 here. So differentiating 2x we get 2 here, and then we integrate e raised to minus 2x, we get this term. So we have minus integration of e raised to minus 2x plus c. So we get is equal to x e raised to minus 2x plus e raised to minus 2x by 2 plus c. So we substitute here the value of v which we have taken. Value of v is 1 by y square. So we substitute 1 by y square and we multiply this equation by e raised to 2x. So all this minus 2x e raised to minus 2x, this will cancel and there will be a new e raised to minus 2x will appear here. So what is given here, 1 by y square is equal to x plus 1 by 2 plus c e raised to 2x is the solution of the given Bernoulli equation. Now we can solve a little more general equation, little more general ODEs than the Bernoulli equation. Namely, if we have a differential equation which looks like dfy by dy times dy by dx plus px fy is equal to qx, then we can solve it where fy is a function of unknown y and px qx are function of x as we know. And this is more general than Bernoulli. In fact, Bernoulli equation is a special case of this differential equation. And how to solve this differential equation? Of course, this differential equation is not linear in general. So the method of solving this kind of differential equation is you take v to be equal to f of y. So it is a new variable v is equal to f of y. differentiate v with respect to x, what we get is dv by dy and dy by dx. So this is, you replace v by fy, we get d of fy by dy multiplied by dy by dx. So what is appearing here, this term also appears in the given differential equation. So you can replace this term by dv by dx, and so our differential equation get transformed to dv by dx appearing here plus px, and this fy is v is equal to qx. So we have this equation here, and this is linear in v, which you can solve. So we have transformed our non-linear ODE into a linear ODE in variable v, and in fact Bernoulli differential equation is a special case of this. In Bernoulli equation, fy is y raised to 1 minus n. If you substitute y is equal to 1 minus n in the differential equation, what you get is the Bernoulli equation. So we see an example here. Of course, this differential equation cos y dy by dx plus 1 by x sin y is equal to 1 is not Bernoulli, neither it is linear, because the dependent variable here y appears with a sine and cos here, so it's not linear, neither it is Bernoulli. But it is of the form which we discussed in the previous slide. So we have this fy to be equal to sin y. So we know how to solve this by, we make a substitution, v is equal to fy. So v is equal to sin y here. Then we take dv by dx is dv by dy times dy by dx. Now dv by dy, where v is sin y, its derivative is cos y times dy by dx. So this also appears in the differential equation. So we replace this term by dv by dx. So what you get is dv by dx plus 1 by x v is equal to 1, which is linear in the variable v, the dependent variable v and independent variable x. It is a linear first order ODE, and we know how to solve it by integrating factors. So here px is 1 by x, so the solution will be given by e raised to integration 1 by x dx. Vx is equal to integration of integrating factor e raised to integration 1 by x dx times qx, which is 1 dx plus c. So you see this 1 by x integration is ln x, or rather ln mod x, but e raised to ln mod x will give you x, and vx is equal to, again we get integration of what is appearing here is x dx. So it is x square by 2, on integrating x we get x square by 2 and plus c. So here we substitute the value of vx, that is sin y here, and divide this equation by x. We get sin y is equal to x by 2 plus cx.